In most cases, of course, we are interested in collecting our own data, and we face this issue of sampling. So now we will spend some time discussing different aspects of a sample and different sampling strategies that we can use to make sure our sample is a good one. What is a sample? Basically, a sample is a limited set of research objects which we use to make general conclusions about the whole population. For example, I'm interested whether Russian people love ice cream. So I could come to the building of the Higher School of Economics at Mysnitskaya and meet 10 people and ask them, do you like ice cream? And then maybe 70% will say yes and 30% will say no. And based on this, can I really generalize to the whole of Russian population? And that's a good question. The quality of my generalization, the quality of my sample will depend on two things. First, how representative my sample is. Obviously, people you encounter within the building of the Higher School of Economics are not your average Russian people. And maybe only 50% of Russian people love ice cream, but 70% of students of the Higher School of Economics. And this difference is called sampling bias, because the property evaluation in your sample, evaluation of some kind of characteristic, is different from that characteristic in a population. Almost always you get some sampling bias. It is inevitable. But there are ways to make it smaller and there are ways to make it more predictable. Today we'll discuss those ways. But obviously having a representative sample is not enough. Also, our sample needs to be large enough. If we only have 10 people, can we really make a reliable, precise estimate of the attitude of Russians to ice cream? Probably having just 10 people is not enough. And actually, your sample can be very large, but it does not mean that it's representative. For example, you can survey all the students of the Higher School of Economics, all the 20 or 30,000 of them, and you will get a very precise estimate of how much they like ice cream, but it will still not be quite applicable to the Russian population. And vice versa, your sample can be very small and it can include very diverse people. So it can be fairly representative, but still it might not be large enough for you to make precise conclusions. So right now we will discuss those two aspects of sampling. Sample size, the very painful issue when our reviewers say, oh, your sample is too small for you to make those conclusions. And we say, what do you mean my sample is too small? How even you dare say this? What's your criterion? And in quantitative methods, there are some criteria. Of course, if you are doing a qualitative study, if you are doing some interview study or you're analyzing some free descriptions, your sample can be very small. There are even case studies where they only used one participant. If you're conducting an interview study, usually your sample size is like 10 to 20 people, because having more is just impossible from the point of view of how much work it takes to conduct all the interviews and to record all the transcripts and to analyze them. So in your master's dissertation, if you manage to do 15, it's a lot. But in quantitative studies where we're using statistics, our sample size depends on a bunch of things. For specific methods of analysis, there are specific recommendations concerning sample sizes, and also it depends on how strong is the effect that we are looking for. So in a couple of meetings, we will start looking at those issues of effect size and statistical power, and we will find out how we can actually calculate the sample size that we need for our own studies to please the reviewers and to make sure our conclusions are precise. But before we delve into that, today we'll mainly focus on why is sample size important and how does it affect our statistics. There is this law which is called the law of large numbers. It was discovered by different mathematicians in different countries independently of each other. And this law, explained in simple terms, is the larger is your sample, the closer are your estimates of sample properties to their values in the population. So if you survey 10 people and ask them whether they like ice cream, your estimate might be actually fairly far away from the real attitude of Russian people to ice cream. But if you survey 100 people or 1,000 people, your estimate is likely to be much more precise. And the deviation of your sample estimate from your true population value is called sampling error, or sampling error. Here on this graph at the bottom of this slide, you can see an illustration which comes from a very simple study where people are just throwing a coin many times, and then for each amount of trials, they measured the excess of heads over tails. Obviously, you're supposed to get a 50-50 distribution or a zero excess of the number of results where you get heads and the number of results where you get tails are supposed to be exactly equal. But as you can see, if you throw your coin maybe 10 times, the difference between heads and tails can be quite huge. And even if you throw a coin 100 times, this difference can be quite substantial. It is only when you throw a coin maybe 250 to 300 times that the results become more or less stable, and you can be more or less sure that this estimate of whether the coin is well equilibrated, whether this estimate is good enough. So this outcome of throwing a coin is basically a random variable. It takes different values in different observations and in different samples. And right now we'll take a look at ways we can describe random variables and ways we can use them in our research. So no matter what it is that you are measuring, your variable can be discrete or it can be continuous. If your variable is discrete, it can only take specific values. For example, you throw a coin and the result is either heads or tails. Or if you ask a person to reply on a scale from 1 to 5, how much do they like ice cream? The answer will be 1 to 3 or 4 or 5 and nothing else. But sometimes we also get continuous variables when the result can take basically any value. For example, you are measuring a person's height, or you are measuring a person's income in rubles, and they can give you any value. And sometimes the same variable can be represented as discrete or as continuous. People have measured variables for a long time. But compared to the history of science as a whole, this history of measurement is actually not so long. It was only in the 19th century that people started to measure things really systematically, to collect large samples and to try to generalize over these samples using some statistical procedures. And the person who contributed a lot to this was Francis Galton, a British psychologists and geneticists, and he was interested in a lot of different issues, and he was actually quite obsessive about measuring different things. So here, for example, you can see the results of his measurement of the height of 8,500 adults born in Britain in 19th century. Just imagine how much time it took him to get these results. And as a result, he managed to draw this nice distribution. What is a distribution? Basically, for every person, for every height in centimeters, you get the frequency, the number of people who with this height encountered by Francis Galton. So a distribution is basically the relationship between the possible values of a random variable and the frequency or the probability with which each of these values can be found in a sample or in a population. So here you can see that most British people in the 19th century, their height was about 170 centimeters, more or less. But how can you actually describe this distribution? How can you capture the information that is present on this graph? And for this, you need two descriptive statistics. Just two of them, imagine, so simple. The first descriptive statistic which we are interested in is called mean. Just simple arithmetic mean. If you want to calculate a mean height of people in your room, you just measure each person's height and then you average. So this average will be the arithmetic mean. You sum up all their individual heights and you divide the result by the number of individuals in your room. And we are all familiar with this arithmetic mean, which describes the central point of a distribution. A little bit more tricky statistic is called standard deviation. Standard deviation describes how much variance, how many differences are there between individuals in this distribution. And in order to calculate this standard deviation, you need to use a formula shown below. How can we understand this formula? Standard deviation is a square root of the variance. And variance is mean squared deviation of each value from the sample mean. So you measure each person's height, you calculate the difference between this person's height and the average height in your room, and then you square this difference, you sum up all those differences, and you divide them by the number of individuals in your room. Variance is a very commonly used statistic, but unfortunately it's not very convenient because it is a squared difference. So the variance of your height will not be measured in centimeters, but in square centimeters, which is actually quite weird. So this is why we use usually standard deviation, which is square root of the variance, and it is expressed in the same units as our original data were expressed. So the square root of variance is your standard deviation. And it's calculated in slightly different ways for a complete population and for a sample, so don't be scared if you see this minor difference in the formula. It only makes any difference in very small samples. So why are those two descriptive statistics important for us? Because they are enough to describe a distribution if it is normal. And it was the great German mathematician Carl Friedrich Gauss who discovered early in the 19th century that if you measure any kind of variable that is determined by many other random variables, by many random processes, you will see that this distribution follows the same function, which is described by this scary looking formula, which I don't expect you to memorize. I don't remember it myself. So it's just for illustration. For people who are more humanities oriented, this shape is called the Gaussian curve, or the bell curve, or the normal distribution curve. And Carl Friedrich Gauss proved this central limit theorem, that if you average many different random variables for measurements for independent observations, you will always get an approximate normal distribution. You can see different examples of normal distributions here on this diagram. They are different with respect to mean and standard deviation. So here on the diagram you see sigma squared. This is variance. It's squared standard deviation. So if you take a square root, you'll get standard deviation. So these two statistics are enough to define a normal distribution. The mean of a normal distribution determines its center position. Sometimes it's also called shift in some sources. So here, for example, you can see that the blue distribution, the red distribution, and the yellow distribution have the same mean of 0, and the green distribution has a mean of -2. And standard deviation describes how widely a normal distribution is spread. So for the blue distribution, the variance is 0.2. The standard deviation will be something like 0.440 something. It's very small, and you can see it's very condensed. Whereas for the yellow distribution, the variance is 5, and the standard deviation will be 2 point something. So it's quite large, and you can see that this distribution is spread widely. And the red distribution has a mean score of 0 and a variance of 1 in standard deviation of 1, and it is called a standard normal distribution, which we are very often interested in for some interesting reasons. But before we take a look at those reasons, let's remember two properties of any theoretical normal distribution. First of all, a theoretical normal distribution is always symmetrical around the mean. If you calculate a mean in the sample or in the population, you are supposed always to get 50% of observations, 50% of individuals with scores above the mean, and 50% with scores below the mean. And the shape of this distribution will be exactly symmetrical. And the second property is that this curve asymptotically approaches horizontal axis but never touches it. So theoretically, it is possible to encounter even very extreme values. For example, if you are measuring the height of people on Earth, theoretically, it is possible to have a person with a height of 5 meters, even though this probability will be so small that you will never encounter it in the years that the universe exists. But this probability, mathematically, it's not quite 0. It's very, very small, but it's not 0. Of course, this is a theoretical normal distribution. In practice, when we face our empirical data, our distributions don't always look exactly the same. So here, for example, you see scores on a questionnaire measuring positive interjection. It's a type of motivation when people say, I do this because I'm proud. I want to feel proud about it. And you have here scores of almost 1,000 people averaged across 4 items, and the response scale was from 1 to 5. So the values that this distribution can take are from 1 to 5. And you see that it kind of approximates the theoretical normal distribution, but does not approximate it super well. Sometimes there are too many answers, for example, in the range of 3.5 to 4, and sometimes there are too few. For example, in the range between 4 and 5, probably we need a bit more to get this result exactly fit under the curve. So this is why, in order to describe an empirical distribution, we need two more useful descriptive statistics. And it was Carl Pearson who proved that if you have these four statistics, mean, standard deviation, skewness, and kurtosis, you can describe a very large family of distributions. So for most practical purposes, these four descriptive statistics will be enough. Why are we interested in skewness and kurtosis? Because they tell us whether our distribution resembles the normal distribution. Skewness reflects whether our distribution is symmetrical or it is skewed. So here on this graph, you can see that if your skewness is large and positive, it is skewed to the left. If it's large and negative, it is skewed to the right. And for a normal distribution, skewness is always exactly 0. And the second statistic, kurtosis, it reflects the flatness of a distribution. If your kurtosis is very large, it means that there are very many observations whose scores are suspiciously close to the mean. Or if your kurtosis is very small, it means that there are actually some distributions whose scores are suspiciously away from the mean. For a normal distribution, kurtosis is exactly 0. So there is a perfect balance between the scores in the middle and on the tails of this distribution. This is why when we encounter some empirical distribution, we typically calculate these four descriptive statistics: mean, standard deviation, skewness, and kurtosis. And if our skewness and kurtosis are acceptably close to 0, we can say, okay, this is fairly normal distribution. So here, for example, skewness and kurtosis are both below within the range of -1 to 1. So we can say, okay, this is approximately normal distribution. And why do we even care so much about this normal distribution? Because this normal distribution has some very interesting properties and some properties that are very useful to us as researchers. No matter what scale you're using, you can always convert your units of measurement to the units of standard normal distribution. In your sample, you can always calculate mean and standard deviation. So no matter what, how large your mean is and how large your standard deviation is, if your distribution is approximately normal, you will get 68% of individuals in the range from -1 to 1 standard deviation away from the mean. So for example, if your mean for your IQ is 100 and standard deviation for your IQ is 15, you will always get about 68% of all individuals in the range from 85 to 115. And you will get 95% of all the individuals in the range from 70 to 130. This is why 70 is commonly used as a criterion for mental retardation, and 130 is used as a criterion for exceptionally high intelligence. So for every person, if you just know the mean and standard deviation in a large sample of people, for every person you can always interpret whether their score is high or low compared to this sample. And also for every normal distribution, you can always be sure that 95% of all observations fall within the range of -196 to 1.96 standard deviations away from the mean. So it's almost equal to 2. As a rule of thumb, you can use 2 standard deviations away from the mean as a rule of thumb for 95% confidence interval. And why is this confidence interval important? Because 95% of all results will fall within this range. And if a result falls outside this range, the probability is only 5% that it belongs to this sample. So this result might be considered as a little bit potentially anomalous or strange or weird. This is why we often use these confidence intervals, because they allow us to determine that this particular person might be actually different from this sample of individuals because their score is outside the 95% confidence intervals. There is something very special about them. And for every scale, you can actually standardize this scale and convert your result to units of standard normal distribution. If your original score was normally distributed, you can always calculate this z-score using this very simple formula. From each person's score, you subtract the mean score in your sample, and you divide the result by the standard deviation in your sample or in the population. And as a result, you get a z-score which reflects the position of this person on the normal distribution on this beautiful diagram. So if your z-score is 0, it means that this person is exactly in the middle of the normal distribution. And if their z-score, for example, is 1, it means that about 85% of individuals have lower scores, and only about 15% of individuals, maybe 16%, have still higher scores. And you can use special tables to get these percentile values for different z-scores. And this is actually very helpful when we want to make some inference about an individual. For example, if we look at the data of Francis Galton, who measured all adults born in Britain in the 19th century, and we can look at Peter the Great, the Russian Tsar Peter the Great, whose height was 203 centimeters. We can actually ask a question: how does he compare to Galton's Brits? Obviously, it would be better to compare him to 18th century Russians, but unfortunately we don't have data for that period because the first systematic measurements of people's height were conducted in Prussian army at the end of 18th century, and the first really good data come from Francis Galton. But we can use Francis Galton's data to find out whether Peter the Great's height was kind of normal or anomalous, how likely we were to discover a person as high as Peter the Great. And in order to do it, we need to convert his height to z-score. In order to do it, we need to know the mean and the standard deviation for Francis Galton's original sample. And we know those two wonderful statistics, so we can apply this simple formula. We subtract 170, which is the mean for Galton's sample, from Peter's height, and we divide the result by standard deviation. As a result, our z-score is 5. So if you look at the diagram, you see that 5 is not even on the picture. Normally, we are only interested in the values from -3 to 3, because values outside this range are very, very unlikely. It's less than 1 in 1,000 that you are likely to get a value as far away from the mean. So for Peter the Great, for this value of 5, you can actually calculate what are the odds, what is the probability of finding a guy this tall in 19th century Britain. And you can easily use Excel for this. There is a wonderful function, norm stdist, which for every z-score gives us the cumulative probability of finding an observation with this or a higher or a lower value. And for Peter the Great, you can see that the odds of finding a guy this tall are like 1 in 0.43 million. So in the 19th century in Britain, there were maybe at best 10 people like Peter the Great. And that's the reason why he was called great, because he was exceptionally tall. And maybe that contributed to his success as a czar as well, because he was obviously a miracle. So this is the procedure that we can use to interpret any kind of individual score. And very often we use it in psychology because researchers usually publish only means and standard deviations for their scales. And then when we get an individual score on this scale, we can use this mean and standard deviation to get a z-score and to arrive at a meaningful interpretation. But of course, those statistics, mean and standard deviation, are measured in a sample. Are they precise? Every time we measure a mean score, the precision of our measurement is dependent on our sample size. And in order to quantify this precision, we need to introduce a statistic which is called standard error of the mean. Imagine that you are measuring the same mean height in a sample of 20 British people. Every time you will get a slightly different mean score, and you also get a slightly different standard deviation. So in order to find out how widely are the results supposed to differ, you can calculate this standard error of the mean. You just take your standard deviation in your sample and you divide it by the square root of your sample size. As a result, you get this standard error, which is basically standard deviation of results from different samples that you are supposed to get if you conduct this study, if you conduct this measurement many, many times over. And we can compute a confidence interval. We take our mean, and because we know that about 95% of all observations are supposed to fall within the range of ±2 standard deviations away from the mean, we know that the true value for the population is supposed to lie somewhere within the range of ±1.96 standard errors away from your estimate in your sample, in most cases. And this way you can actually find where is the true score supposed to be. But obviously, how wide those boundaries are, it depends on how large is your sample. There are very many different simulators online when you can play with those statistics. This one comes from some kind of biological study. People were interested in the average weight of a fish of certain species. And imagine that different researchers catch samples of just 20 fish of this particular species. And you see that every time the mean, which is shown on this diagram as a little black point, the mean actually jumps a lot from study to study. Sometimes the estimate is as low as 500 grams, and sometimes it's actually fairly high as 700 grams. And the confidence intervals, they are shown as little bars around this sample estimate. So people calculated in their sample mean and sample standard deviation and divided the result by square root. They divided the sample standard deviation by square root of sample size, and they got this standard error, and then plus minus 2 standard errors away from the mean gives you the 95% confidence interval, which is supposed to reflect the location, the possible range of the true population mean. And as you can see, this confidence interval is fairly huge because the sample is very small. But what if researchers catch a larger number of fish, 200 fish, and then you can see that the confidence interval becomes much, much smaller. And the mean scores in the mean estimates on different samples, they don't really jump as widely. You will not find as extreme estimates as like 500 or 700 grams. They will be generally around the true population mean. But obviously, the amount of resources that is required to catch 200 fish is very, very huge. So probably you won't be willing to get such a large sample. So in general, the larger is your sample, the smaller is your standard error, the more precise are your estimates of statistics. So here we took a look at the standard error of the mean, but basically every statistic that you calculate in a sample has a standard error. If you calculate a correlation, it has a standard error. If you calculate a difference between two groups, it has a standard error, and this is used to judge whether the result is significant or not. So, of course, you can get a very, very large sample if you are as obsessive as Francis Galton, and if you calculate standard error for his very huge sample, you will see that the standard error of the mean for the British people's height is only 0.07 centimeters, so it's smaller than 1 millimeter. Basically, it's even more precise than the precision of a ruler, which is used to measure this height. So this is extremely high precision. And probably, normally we don't need such large samples. But whenever you are thinking of a sample size, think about this curve. It always has the same shape. First, it drops down very quickly, but then it kind of tapers off. It's like in economics, there is diminishing marginal utility. The larger is your sample, the smaller is the contribution of every individual person, of every additional participant to the precision of your measurement. So obviously you need to decide a point where you should stop to avoid wasting your life and your valuable time improving the precision when it's already precise. Probably too large a sample is also not really needed, but of course, if you're lucky, maybe you can get a large one. So if we summarize in short our discussion of sample size, the more the better, because there is the law of large numbers. The larger is your sample, the closer are your sample estimates to the true estimates in the general population. But also, there is diminishing marginal utility of each additional unit, of each additional observation. So our sample size needs to be optimal for our research goals. And in a couple of meetings, a bit more, in our topic number 7, we'll take a look at the issue of statistical power, and we'll find out how can we calculate the exact sample size that we need to test a certain hypothesis with a certain degree of precision. So stay connected and you'll learn how to do it. But size is only one aspect of our sample.